All right, so over here, we're going to breeze through equilibrium at quantum speed. Okay, so equilibrium. When we're talking about equilibrium, we're talking about what's known as a dynamic equilibrium. Okay, there are two types of equilibrium. The first is going to be that normally people think about is a static equilibrium. That is where where nothing is actually happening. Nothing happens. It just basically stops. It's saying here, it's inferring that the reaction has come to its endpoint, okay? And in chemistry, 99.9% of reactions do not ever come to their end point. Most reactions, if not 99.9% of them, are in what we would call a dynamic equilibrium state, where products are being reconverted into reactants, and reactants are being converted into products. And so when we're talking about a dynamic equilibrium, we're talking about this. This is our definition for equilibrium. You should jot this down, take note of it. That is when the rates, and we talked about that in chemical kinetics, the rates, that is what is known as the change in molarity over the change in time. Remember that? Ooh, bad move there, Stephen. Rates of, so that is the molarity over a certain period of time. So the rates of the forward and reverse reactions are now stable, and the concentration is not changing at all, okay? So rates are in equilibrium, but not the molarity, okay? You could have A and A yielding B, and you could have, 4 moles of B, and you could have 3 moles of A, and they could still be in equilibrium because we're dealing with the rates, how fast that reactant is turning into the product, how fast that product is turning back into the reactant. And so we're not talking about the molar concentration. A lot of people confuse that, and they think, oh, it's the same amount that's actually going to be in the reaction vessel or the system. But really, it's not about the amount at all. It's about the rate of that reaction. So visually, let's illustrate it like this. Let's look at this right here. We have a graph, and this graph is displaying for us a chemical reaction, A and B. A turns to B. And so you have on this side the concentration values, and what you have here is that reactant A starts off at 0.7, and obvious that's molar concentration. And then remember, molar is moles over what? Liters, right? Molarity is moles over liters. So you have a 0.7 molar solution of reactant A, and at beginning point, you have a 0 molar solution of B because there are no products yet, right? But as the reaction moves forward, right, then what you have is the reactant A is decreasing while reactant B is increasing. And so this will at some point, as it decreases down this line and increases up this area where the molar concentration of A goes down to 0.3, right, from 0.7. And then the molar concentration eventually reaches 0.2 for B right here. And then at some point, this molar concentration no longer changes, and that is what's called the equilibrium point. No longer changing in concentration. And what's happening here is that the forward reaction, boom, is happening, right, at a certain rate, and the reverse reaction is happening at a certain rate, but the molarity is staying the same, okay? And that's really how you tell equilibrium. When you reach that point where the molarity just doesn't change anymore. The concentration is not changing anymore. And the rates of the forward and the backward reaction are in equilibrium. And so this is expressing the movement of equilibrium. And you can see that this stays at 0.2 and this stays at 0.3 forever. You can also tell, and I know you love this, you can also tell the stoichiometry of a reaction based on a graph like this. I know you love stoichiometry. You can't get past it. It's chemistry. All you have to do is, when you're looking for the stoichiometry of a reaction like this, you look over here. Where does it start? It starts at 0.7 molar, and it moves down to 0.3. So it starts at 0.7, moves to 0.3. This starts at 0 and moves to 0.2. And so you look for the changes. So this is a change of 4 molar, right? And this is a change of 2 molar. And so we see we can simplify that down to this reaction is in a 2-to-1 ratio, 2-to-1 stoichiometric ratio. And you can use that later because we use molar coefficients in our equilibrium constants. And so that's a general understanding of the definition of equilibrium and how to view a graph and really see what equilibrium would look like on a graph and be able to pull out the stoichiometric molar ratio for that. So let's move on and let's talk about the equilibrium constant. Okay, the equilibrium constant, it can obviously be expressed, because I've written it over here already to move through this super fast. The equilibrium constant, and remember when we're talking about constant, we are talking about K, lowercase k, not capital K, because that's Kelvin. Sometimes I'll mess that up, and I do apologize. But we're talking about this constant, and that can be written in one of 3 ways for equilibrium. It can be written in KEQ, which obviously EQ stands for equilibrium. It can be written KC. See, these are interchangeable right here. And so KC stands for the concentration constant, concentration, right? And then KP stands for the pressure constant, okay? And KP deals with gases only, okay? Gases only. So when we're looking at equilibrium constants, KEQ, KC, or KP, we need to understand that this K concept right here, really helps us to quantify the concentration of products and reactants when at equilibrium, okay? And we'll talk about why that's important later as we go through the reaction quotient. But for right now, you need to know that the KEQ or the KC is helping us to quantify mathematically the concentration, how much of a solvent, how much of a solute is in a solvent at any given at the point of equilibrium in that reaction. So what you're looking for here is this understanding. K helps us to quantify concentration values at equilibrium of the products and the reactants. Now, K is different for different reactions and different temperatures. A lot of people think constant is going to mean that this is the same number for every reaction. It's not. Just like we talked about in acids, bases, just like we talked about in kinetics, this constant is for specific reactions, right? Specific reactions, and at different or literally same temperatures. If it's a different temperature is the only thing that's going to affect K. Remember that. Temperature is the only thing that is going to affect K. Okay? Other things will affect the concentration of gases, and we'll talk about those effects later, but K is only affected by temperature. You need to remember that. K is only affected by temperature. And notice this too, you will never have a negative K value. Never have a negative K value, okay, for the equilibriums constants. So now we know this is a speedy process. When you have a K constant, what you're going to do is you are going to set that example KEQ or KC or Kp, that's going to be set equal to the concentration here in molarity, moles over liters, the concentration of the products over the concentration of the reactants. Okay, that could be raised to some stoichiometric coefficient. So if we take this equation right here, this generic equation, we can see that we can write this, say, let's write the Kc expression of this equation. So Kc equals, and we're going with the products, so we got the concentration of C raised to the C. We got the concentration of D raised to D raised to the D. And then we get the concentration of A raised to the A, and then B raised to the B. Some stoichiometric coefficient goes here. Now, when we talked about kinetics, these coefficients, or these exponents were the rate law, right? The rate order, okay? But here, we're talking about stoichiometric coefficients. Stoichiometric coefficients. You can't get away with it. Now, what I want to suggest here, too, that if A was considered a solid and the rest of them were gases or aqueous, then A would actually be eliminated from this K expression. Because solids, let's just write that down here, solids, solids and liquids are omitted from K constants, especially in equilibrium. Some other equilibriums do involve solids and liquids, but not for equilibrium, and so we're fine on that. But solids, just know this, that if you see, and you'll always see these states here, but if you see the states and you got a solid or liquid, omit them from the K expression. Remember, K expression has math being eliminated. No math in an expression. You're literally just writing the generic form of that equation. So this is obviously stoichiometrically impacted. Well, I showed you that up here. So that is molar ratios and coefficients. Do not forget stoichiometric coefficients. Don't forget it. You'll essentially go through a problem, get it perfectly right, but forget the coefficient, and that will be wrong. So make sure, just get it in your mind. Put a bracelet on your wrist for the next week and snap it every time. When you snap it, like think coefficient. Okay? So this is the K constant written out. This is what the K constant does. This is where the equilibrium constant is. So you have these three ways of expressing the K constant: KEQ, KC, or KP. This is stoichiometrically impacted. So let's talk about what a value of K would do to a chemical equation. So if the K constant, let me make this lowercase. If the K constant is greater than 1, okay, then the products are going to be favored. What that means is that if you have a K constant after you have done the products over the reactant equation, if that number turns out to be over 1,000, it seems big right now, but when we get into these concentrations, it's really not that big, and you'll see what I'm talking about later. But when you get into that, over 1,000, what you're going to see is that reaction is going to go to the right, and there's going to be more products than reactants. Okay, the products are favored. This is a key word, and that is when the K is over 10 to the third or 1,000. Okay, and then the reverse of that would be obviously true if the K value is lower, -3 to 10 to the -3 than 1, then the reactants are going to be favored. The reactants are going to be favored. That means that there's going to be more at equilibrium. Remember at equilibrium, at equilibrium, the concentrations of these products and reactants can be different, but the rates are the same, okay? So the K less than 1, 10 to the negative third, you have a reactant that is, reactants are favored, okay? Now, if K is somewhere, say, for example, let's just take the midpoint right here, 500. K turns out to be 500, okay? Then what that's going to mean is that you are going to have both reactants and products available at any given point during that chemical reaction. Now, this will, because it is going towards 1,000 at the 500 mark, you're going to have more products. You have more products, but it's still going to be at any given point. You could look in there and you're going to have about the same amount of products and reactants if K is in the middle of that 1,000, 10 to the third, 10 to the negative third, okay? So, again, what could we expect if we had a K value of, let's say, 100? 100. Again, that is less than 1,000, and it is less than or more than 10 to the negative third. And so, again, we would still have both reactants and products. Both reactants and products. Again, you'd probably have a slightly bit more, like you might have 2 here, and you might have 3 here, right? Products and reactants. But like if you had 1,000, if you had over 1,000, that K is going to be like, say, for example, you have 2 here, and then on the product side, you're gonna have so many more over here, and that is still in equilibrium. Why? Because it's the rates that are making the most effect here in equilibrium. The concentrations are going to remain the same, okay? But the rate is what we're looking at. So remember this, look back at this video, the K greater than 1, and you can think about it like this. Like if you set it up, K is greater than 1, you could just draw your arrows in here and think, oh, it's going to the right. It's lying towards the right. Not lying as far as telling a fib, but it's lying towards the right. And then you could draw your arrows in here, and you could say, oh, K is less than 1. And so this is reactant favored, and it's the reaction is lying to the left. Okay, lying to the left. So let's keep going. What I have here is one of my favorite chemical reactions. 2 carbon solid plus O2 gas is going to yield in equilibrium, meaning the rates are of the forward and the backward reaction are stable, and the concentrations of these are no longer changing. Now, this is a reaction where 2 carbon solids plus oxygen gas is yielding 2 carbon monoxide gas. And so when we write this KEQ expression, why did I not put carbon in? Because it is a solid. It's a solid. Therefore, the only thing that I've got in my K expression, my KEQ expression, is going to be the carbon monoxide. And look where I've got this 2. That is the going to be the exponent because it is the coefficient. Notice there's no exponent on this, so I'm just looking at the concentration of O2. And let's just put some random weird numbers on this. So you have KEQ. Once you write out this expression, you have KEQ. That's going to be equal to, say, for example, we have at the top the concentration of carbon monoxide is going to be 0.32 molar. Okay, 0.32 molar. Now, the concentration on the oxygen at the bottom is going to be 0.16 molar, okay? Now what you would do is obviously to find KEQ, you would simply divide these, or divide this 0.32 by 0.16, and I think that obviously gives you 2. What is that? Yeah, it gives you 2, I think. I suck at math, so let's just go ahead and say that. That'd be the 2. So K would equal 2. And you would have your equilibrium constant at that point, okay? Now, we talked about pressure. This is a little difficult and a little weird to understand at first, but you'll get it. Just think about it. So this is our Kp expression. We use the same exact expression for this process as we do for the Keq or the Kc. So it's the same general product over reactants, except for in this, we are trying to discover the pressure at equilibrium. Up here, we're trying to discover the concentration, and here we're discovering the pressure at equilibrium, okay? So you can't get away from this either. PV equals nRT, okay? That is the ideal gas law. PV equals nRT, ideal gas law. And in this case, you are always going to use 0.0821. I rounded that one up because it's 0.08206. So I rounded that up. You can do whatever. It's going to give you the equation anyway. So that is going to be the R. And the R is what's called the gas, constant. The gas constant. And so the T is going to stand for temperature. The N is going to stand for number of moles, right? The P is obviously going to stand for pressure, and then V is going to stand for volume. And so this is how we're going to figure this out. In order to discover the pressure from a solution, you have to turn this into molarity. You have to turn it into molarity. You have to end up here. The only way to rearrange the ideal gas constant to do, or the ideal gas law to do this, is to recognize that what is going to give you molarity? Well, number of moles, right? And the volume. Remember, number of moles over liters. Liters is measured in volume, right? And so what you do to get this equation, this is your equation when you're trying to figure out the pressure of this at equilibrium. You use P equals M, molarity, capital M, R, T, and you just plug your numbers in and chug your equation out. And so what I did was I just showed you in these two steps how to get here. And I showed you that because you need to know molarity. You need to know that this equation is totally movable. You can flex this equation in so many different ways in order to get the pressure. So what we have here is this constant, again, 0.0821, and that is the units are liters times ATMs, atmospheres, moles per mole Kelvin. Okay, and the temperature, remember, temperature is the only thing that is going to affect the K constant, so you need to be watching the temperature when they give that to you. My bad. Let's come back here. One big thing you need to know about this is when it's asking you for pressure, if the stoichiometry, what is that? That is the coefficients. If the stoichiometry is the same on both sides, then the Kp is going to be equal to the Kc, and you don't have to figure out anything after that. Just know that if they ask you which one of these are in equilibrium, and you can look through an equation and see that the number of moles on the reactant side is equal to the number of moles on the product side, then you will be able to say that is equal to the Kp, the pressure, is going to be equal to Kc. I'll show you that equation in just a minute. I know this is a little difficult. I'll send some videos out specifically working through practice problems, and we'll do one down at the bottom. But notice this. Say, for example, we have to figure out the Kp because the Kp is not equal to Kc here because our molar ratio is different, right? If we go back up to our equation, we've got 1 mole of oxygen. We're leaving out carbon because it's solid. We got 1 mole of O2 gas, but we have 2 moles of CO, carbon monoxide. And so when we put that in, we put our coefficients as our exponents, we see that the stoich is not the same. So Kp is not going to be equal to Kc. Even though we would think, okay, man, if it's constant in pressure, then the constant in concentration would probably be the same too, but that is not the case. And so if you're given Kp and then they ask you to find Kc, or if you're given Kc and they ask you to find Kp, this is the equation you're going to use. That's going to be Kp, K pressure, equals K concentration, times RT, times the gas constant, and then the temperature that they give you, and that's all raised to the power of the number of moles, or the coefficient. Okay, so inside of this one, the coefficient would be 2, raised to the power of 2. Okay, right? So this is what it'd be raised to. This is pretty simple. If you just memorize these equations, you don't really need to know the concepts too much right now. You just need to know these equations, and you'll be able to get at least some points on that AP exam as we go. Just know this, that pressure and concentration really don't have to be the same if the actual volume is different, right? Like you could have the same amount of concentration in a larger vessel. If the pressure of the vessel increases, then the pressure is going to decrease, right? And so you could have the same amount of concentration in here, but the pressure is going to be different. Okay. So, let's see. What did I put this here for? Oh. We have, say we're looking at this. Actually, that's